All right, so now who's together, but I will give me some time, so take a photo more. So, the speaker is, board that I from, I think we all, Tommy, and a lot of them, yes, and I don't know, we talk. It's what that our fund, that helps mother, and continue to empower all of it. Very, very.
Yeah, first I'd like to thank the organizers for the invitation and the chair for introduction. I'm sorry for the long title. And I, yeah, I apologize. I was not here yesterday. This is a problem when the meeting is on campus and you cannot find excuse. So we should lock ourselves in some remote place so that no one can go out. I think we did that for retreat a few times. Okay. Yeah, and I'm also affiliated with the NCTS. I'm a coordinator for TG 4.2, I believe. Okay, so this is one of the projects that we have been working with physicists and chemists and mathematicians. It's a very small problem. Okay, so yeah, I'm not sure how well people understand the field of chemical physics. So I decided to use the example of water, right? Which is my favorite molecule. I spent a good part of my career just to study structure of ice. And these are the vibrational spectrum of water in various phases, right? Just in case you don't know, water is H2O, and the red ball is oxygen, and you have two hydrogen, right? This is the origin of life. I don't know how to justify, but when people see water in space, they say origin of life. When they see glycine, they say origin of life. uh, I can see the possibility. I just don't see the link. But water is such a cute small molecules that give us so many wonder, right? So if you want to understand the vibration of water, and this is in the textbook, right? We start with normal mode. I remember in the classical mechanics, we learn how to diagonalize the potential surface to the second order, you get the normal mode, right? So water has H2O, you can deuterate and you can partially deuterate. These are what chemists can do. So for chemists and not chemists, I think this is pretty much what everyone can do to understand the structure of tiny water molecule. How do you know water look like this, right? I think in high school, kids are told that ammonia look like this, nitrogen and three hydrogen, and water is like this. And in the high school, we are forced to memorize which one has larger angle or what, right? And I think in this audience, I always share this personal feeling, right? As a high school student, I hate chemistry. I'm pretty sure I get 99% the same feeling in this. But the reason may be different, right? For me, it's chemistry is a course that in the textbook, you are taught the rules. In the exam, is all about exceptions, right? Right? As a very naive high school student, should I trust what my teacher are trying to teach me? If I do, I'm going to fail the exam, right? And only as I grew older, and I realized why it has to be that way. Okay. And I hope I can share. So I sort of forgave my high school teacher when I turned sort of like age of 50. And I hope you can share the same feeling. Don't blame your high school's chemistry teacher afterward. And the reason I chose physics in college, not because NTU physics ranked higher, it's my high school physics teacher did not teach. So I had to study myself, right? So sometimes the best way of teaching is not to teach. All right, so I think enough joke, but yeah. Spectroscopy is what chemical physicists and chemists and material science try to know the structure and the local environment of a molecule, right? And I'm going to, I think my research is I try to understand why these simple rules come about and when they break down. Okay, as a physicist, and I think we like simple models, right? Most of you work in model Hamiltonians, but all these Hamiltonian are only approximately correct to describe the real words. Okay, Yeah, so water can form different phase. So if you have a vapor, you see these many peaks. And when it's condensed to beautiful regular ice, you see this light blue. And the ambient liquid phase give you a broad band, right? And you can see many papers, and they just try to justify if this is a experimentally observed spectrum, it has many subtle features. And many simulation will carry out or to say water in liquid phase of different environments. You can forget about the jargon. Everyone is little bit different. And based on the normal mode picture, they say, this group of water is under this circumstance, and that group has a stronger hydrogen bond, etc., right? And how much should we trust this interpretation, right? Because all the material properties come out of this interpretation. I give you the simplest example I can think of, and that can lead to important consequence if the interpretations are wrong. Right? So for chemical physics, this is our Hamiltonian, right? We have a bunch of electrons, and we have a bunch of nuclei, and they are interacting through Coulomb interactions. Of course, some detailed interactions are missed, right? So this is the working Hamiltonian, and the whole field of quantum chemistry is to take Born-Oppenheimer approximations. That is to take the wave function in this form. So we solve the electronic part first. And this gave rise to DFTs, etc., these theories, right? And this also gives us the idea of potential surface. Yeah, so now this is a common practice. You can use these packages to solve electronic Schrödinger equations. Electrons are very quantum. This is what everyone agree, right? They are fermions, and all the tricks go into this field of quantum chemistry. And there are many commercial softwares that you can use. That's not my research. My research is after this potential surface, and if we have to, whether we have to solve Schrödinger equations to get the vibrational dynamics. Okay, a lot of people use ab initio molecular dynamics nowadays. Is you get the potential surface or get the gradients out of this DFT, and you can propagate equation of motion classically. Okay, but in some case, I hope I can show you important case that we have to solve this nuclear, the degrees of freedom using quantum mechanical, and there are a lot of dynamics, and that can be observed directly by spectroscopy, infrared, microwave, etc., etc. So basically, we are computational chemical physicists trying to connect this equation to observables, and there are a lot of things that are not trivial, but that's basically what many of us do, right? So if you solve the quantum chemistry problem that gives you this potential surface, right? Diatomic molecules at certain shape, but potential surfaces are not directly observables, right? Spectroscopies are. And that's the missing link that we need to close the gap. Okay, so in my other work, when I try to pretend I can do useful research, we work on sugar. Okay, that's another set of another set of talk. Yeah, so if you think of a diatomic molecule, right, and the basic idea to describe vibration is harmonic oscillator, right? That's the most useful model in physics. And it's realized that diatomic molecule would dissociate, so harmonic oscillator would never break. So even in the 1930s, Philip Small, who wrote the books on mathematical methods, come up with a model called Morse potential, which can dissociate. And this is exactly solvable one-dimensional Schrödinger equation, right? So people knew that Morse potential, right? Harmonic oscillator give this equal spacings. I think that's trivial. Most oscillator give you, and right, the bound states, there are finite number of bound states, and they're a continuum. But if the Morse potential the exactly the same second derivative as harmonic, the spacing of these anharmonic potentials are not equally spaced. I think these are simple model. So chemists have always used these rescaling factors. So if you use a DFT, to simulate the structure of molecules, and you get the second derivative of the potential surface, almost always you don't agree with the experiment. and they come up with a table of scaling factor. Okay, and this paper, I tell you, they are well cited 8,000 times. Why? Because experimentalists can always find a magic number that match their observation. And right, so highly cited doesn't mean it's clearly understood. So if you write a beautiful paper, you cross the field, likely you don't get any citation. Right? So we are always in a dilemma whether we write a beautiful paper or we write a well-cited. Okay, and I think I can do neither, so I somewhere in between. But most importantly for me, it's this one-dimensional picture of between modes and harmonic, the general picture. Right? And so I decided to do a little experiment. Right? I can use this quantum chemistry package to scan potential surface. Right? This is something everyone can do. So there are 3 normal modes of water, and I can scan the potential surface along this normal mode, right? One at a time. And and I use a numerical method called DVR, discrete variable representation, which is standard method to solve differential equation, right? So you solve along 3 normal modes, one at a time, and you see the harmonic value and the numerical solutions are not always going down. Okay, in fact, 2 out of 3 are not. So if democracy works, go by voting, then none of the 2 out of 3 normal modes are not most like. But if you solve the differential equation in 2 dimensions, if I take these 2 high frequency modes and I scan in 2 dimensions, you can see the eigenvalues systematically go down. Right? So dimensionality does matter. Okay. But yeah, so what are the what is the guiding principle that people empirically do the rescaling, which is not obvious to me, but okay, I will not try to answer these questions in this talk. And yeah, so rescaling is a matter of quantitative adjustment, right? You multiply a factor of 0.93 or 0.95. There are other phenomena that you don't get by just rescaling. And this is not an exotic kind of molecule, CO2, okay, right? Which is responsible partially for global warming, whether you believe or not, right? And this is in 1931, Fermi, okay? When Raman spectrum was invented at the time, right? And Raman spectroscopy of CO2 was measured. And back then, there are no computational tools, right? But it's observed where there are 2 peaks rather than 1 in where you expect to see this motion. And Fermi, as a good physicist, came out of nowhere that he wrote down a Hamiltonian, and then he explained, okay, the 0 to 1 transition for these symmetric modes, right, that we call 1, will couple to overtone of another mode. And you can use group theory, and you can write down the phenomenological Hamiltonian. Yes?
What's paper? How many times have to look for?
I don't know. I only remember Fermi was a full professor at age 25 in Rome, right? While we barely start graduate school. Yeah. But you can be sure Feynman's paper are not well cited because it quickly was written to a textbook, and no one cited the original paper anymore, right? Yeah. So you want to kill your good publication, for the citation of your publication, write a book, but you may get rich. Right. So Fermi was able to see through the underneath physics, right? The coupling. So he said that this coupling, whatever that is, right? Then the coupling means this off diagonal terms, and then you can, based on this model, then you can decode the coupling, right? And CO2 triatomic molecule, not too hard, but when you think of a molecule of reasonable size with 10 atoms, you have to be very good to come up with the underneath physics, right? But everything is computable if we follow Dirac's Dirac's quote. Everything about chemistry is known. All it takes is solve that differential equation, right? And 100 years, almost 100 years later, we are struggling to do the same. So making approximations, appropriate approximations, to explain the physics, right? Yeah, you have to make approximations to throw away a lot of detail of making the computation to go, right? That's easy. The difficulty is to keep the same accuracy, right? And I think that's what all of us are trying to do. All right. So in the favorite molecule of mine, water, the same phenomena. So this type of model is called Fermi resonance. Okay, that means right, two vibration modes, the fundamental of mode one coupled to the overtone of two. But actually, they are doubly degenerate two. There are two quanta states. Only one can couple by symmetry. I will not go into the detail. But in water, the same phenomena has been proposed. Right? So the overtone of the bending can couple to the fundamental of symmetric stretching. I'm repeating what's known in the literature, and this is also known as Fermi resonance. This is a general phenomenon in chemical physics, except, right, a paper will tell you, this coupling between the fundamental symmetric stretching, which is right down in red, coupled to the overtone of the bending, and the order magnitude is about 25. This is like the chemistry textbook, right? It's going to break. Okay. And a couple of years ago, we studied simulate a system, water forming hydrogen bond. If you don't know hydrogen bond, I can explain to you later, with a amine. And this is experiments done in gas phase. And we choose this because this system has high symmetry. So there's only one way to bind, as far as we can think. And the experimental spectrum came out in black. Okay. So, and in this region that described by red, there are only two normal modes. Okay, that makes sense to chemists. One is the free OH, one is hydrogen bonded OH. And the puzzle was, why did they see so many peaks? Right? So the example of CO2, okay, I'm going to insult some material scientists. I hope none of them are here. CO2 fixation is such an important question, right? Many materials are designed as catalysts to absorb CO2 to turn into useful fuel, right? You don't have to agree, but that's what people do. And I attend some material science meeting and they say, this is my Raman spectrum and my CO2 absorb because there are two peaks. So there has to be two kinds of CO2. Okay. They didn't know Fermi resonance. So I had to say, okay, one, your CO2 did not absorb because it's gaseous. There are not two types of CO2. There's only one. So if you don't know this fundamental principle, you can, and all the consequence, the argument of that paper is wrong because the basic assumption that they start, that they see CO2 absorb on surface is wrong just because they don't know this fundamental resonance. And these are in the textbook. Nowadays, I think we should use AI to do the pre-screening first, right? So these notions are important because material scientists use spectroscopy to validate their arguments and to deduce everything that they make they make the claim, right? So when astronomers tell you what the molecules are out in space, they cannot take samples. The only way is use telescope, spectroscopy, right? How do you know the molecule is there? You use telescope to record spectroscopy, but you have to do the inverse problem, decoding what is there, right? And that's the power of spectroscopy. So getting back, the textbook tell us that the coupling is 25, but this Fermi resonance only give you two peaks. The puzzle we have is why do we have so many peaks? And even I say, okay, this is the Fermi diet, this is not 25, this is 50. So the question I have is who decide such coupling schemes? Right? In a molecule with n atoms, you have 3n minus 6 vibrational degrees of freedom. And you can just simply compute the density of state. It's very high. There are thousands. So which one coupled to who? Who decide which mole couple? No, that's a question that we have. And all of this can be computed. Okay. Yeah, I think in the interest of time, I'm not going to share too much detail on the domain knowledge, but this is a typical scenario when it comes to you talk to experimentalists, and they have a lot of puzzles on the experimental spectrum, but they need to know the structure, right? To continue argument. Okay, so I think I have 10 minutes left. And I'm not even started yet. Right. So if you can scan the potential surface, you use this DVR, discrete variable representation. This is nothing special, right? You can solve this differential equation. You choose a basis set, you convert differential equation to a matrix, you diagonalize, right? The problem we have is the dimensionality, right? This method scale as number of grid point to the power of dimensionality. And this is classic, one of the classic case of curse of dimensionality. When D is 1, 2, 3, 4, we can do it. Beyond 6, 7, we hit the wall, right? And more importantly, for chemical physicists, this is different from many problems in condensed matter. We don't know the Hamiltonian. We have to approximate Hamiltonian. We have to, right? When you go to the jungle to hunt the monsters, we don't even know what we are going after. So the first question is, we have to approximate Hamiltonian. And remember, compute every energy or gradient. That is another set of Schrödinger equation. You have to solve the electronics Schrödinger equation. All right, so we can do this when the dimensionality is not high, meaning 5 or 6, as long as you are willing to spend the computer time, right? And yeah, I think I'm going to skip this. This is yeah, so typically the system we are dealing with, when I was young, I studied ice and I studied cluster water. And when I'm aging, the size shrink. Okay, right. So now I study system with one water forming hydrogen bond with the simplest molecule, one atom. So this is a headlight. It can be iodide, bromide, chloride, right? So because this small system, all degrees of freedom are 6. There are only 6 normal modes. And these are experimental data, okay, that were measured at the different times. And yeah, we use our machineries, which is I described in the previous page, right? We can scan the potential surface. If you are willing to say every degrees of freedom, you use 10 grid points, 6 degrees of freedom, big deal, 10 to the 6, 1 million. Right, you can throw in computer, you can diagonalize a sparse matrix of a million by million. I wouldn't say effortlessly, but in a few hours, you can do it. Now, right, so back then you take a few days, 10 years ago. And now you have GPU that's even faster, right? So if normal mode works, right, this system all have 6 degrees of freedom. You see 6 peaks that are highlighted in red. But we see a lot of additional peaks. And how well is our prediction, right? And these are existing experiments. So no scaling, no fitting, just simply solving the equation, right? There's not much physics to learn. You throw in the computer, you coin the number, you get the prediction, which just validate our algorithms are at least useful. So now, if this method can continue to be ported to systems that are larger, then we have something useful to experimentals, right? And yeah, so next are unpublished results. If we deuterate one of the water, the vibrational coupling change entirely. A chemist, any good chemist, based on the empirical rule, will tell you if you deuterate this free OH, things will not change. But that breaks down in certain cases, and we like to know when this model breaks down, and that's when we need the most next level, more complex model to explain. All right, so I think I'm running out of time. If I want to leave 5 minutes for you to ask questions, after we can solve, right? We are not satisfied. We want to do like Fermi. Okay, can I write down a small Hamiltonian that I can explain without right? Instead of a million by a million, can I use a 10 by 10 matrix to explain this observed feature? And yes, there are numerical methods like the FBR, and I'm sure there are other schemes that that can turn a big matrix. You can distill the information to leave a take-home a small Hamiltonian to explain. And that is something we are also interested in doing. Because in the past, a good chemical physicist have to come up with a phenomenological Hamiltonian with parameter to fit to experiment. We believe using this for algorithms that we develop, we can skip so our tools is have a prediction power. Right. So why is this useful? If we know the vibration Hamiltonian, and we can propagate the Schrödinger equation in time domain, so we can work with chemical physics who use this ultra fast laser to squeeze more information out of Hamiltonian, and which is in the field is a two-dimensional Hamiltonian. So this is something we are working with Zheng Yuanzhong in chemistry and Hayashi-san in the Center of Condensed Matter Physics. Okay. And when the dimensionality is even higher, and this is where the method we have been using for the past 10, 15 years hit the wall, right? And it's the curse of dimensionality, and that they are useful tools in the field. This matrix MPS, right? And I will not go into the detail of this. In fact, we are learning with Gao Yingzhe and Chen Boduan and Zhong Jiamin. They are the TG 4.1. I hope I'm right. The director is sitting here. Okay. Right. And of course, they are deeper math. And this is the project I have with Matthew. And we get funded. We are happy and also nervous. We are happy when we get the money. We are nervous when we have to deliver the results. But overall, we enjoy this journey. It just started a few months back. So I don't have concrete result to report. But yeah, we are having fun. So this is my summary results. For chemical physics, we are usually facing an unknown Hamiltonian, right? So we have to truncate somewhere, and we have to build simple enough models. And just this time, if I teach my student, I will tell them, don't trust me. Whatever rules I'm going to teach you, it will break down eventually. And it's important to know when it breaks down, so we know when it's safe to use, right? So I don't have to be blamed by my students that I'm teaching them the wrong things. And yeah, so this method problem have limitations, and I think the new numerical methods, or not so new, can be used to help us to break the curse of dimensionality. And not only to solve equations, we want to get simple enough physical picture for physicists to digest, so that we can explain experiments without engaging all this heavy machineries. All right, so this is the last page of the scientific part, and I think I want to thank Director He for helping us. So I'm currently the director of CCAN Taiwan Node, which unfortunately is is blocked by this box here. And NCTS partner with Academia Sinica, with the institute I work. We are just across the lake. So if you want to visit us, you're welcome. So we are working with another two TGs, and I think we propose 5 CCAN flagship workshops. They are not formally approved yet, but we are very optimistic we can do it. Most of them are in Taipei, including one in Tsukuba, right? So I think in the spirit with iTHEMS, maybe next time we can also work with the RICAN communities so that one of the meeting can be in Waco City or somewhere of your choice, maybe a scenery place where everyone get lucky and not getting out for a few days, and we can discuss some interesting science. So I'll stop here. Thanking your attention. Thank you. Yes, it is possible. It's been done. to start from first principle, you can solve that Hamiltonian with electrons and nuclei, as long as you make approximations, right? This is repeatedly shown. This is a common routine. It's the scalability is bad. Okay, right. So when you have one water, you have 3 degrees of freedom. That's easy. Okay, and when you have two water, the dimensionality already exceeds what we can do brute force. So what we are doing, in principle, the equations are there. It's how we approximate the systems, taking appropriate approximation, turn this equation into computable limits. Of course, now we can think of using AI to do this for us. I hope that day to AI to replace me is not anytime soon. But anyway, I only have 10 plus years left before I retire. For young people, you have to worry. Okay, right? You have to pick the problem you can do better than AI. And for me, time is running out, 10 plus years. But for you, just starting your career, you have more competitors. Right? Okay, but now the opportunity, a lot of the question we are doing now, I have to admit, the moment very often I think I'm smart, but I read the literature, I think there are 100 people smarter than me in the past, but they didn't have the computer to solve the problem. So a lot of the time I can read the old paper, they have the idea, and they never had the opportunity to do, right? So a lot of the time we think we invent something. So if you want to feel good, don't read the literature. Just think you invented. And you feel bad the moment you read, oh, people came up with all this idea, right? And to keep your psychological health, you say, I'm not doing the wrong thing. Okay, right? And the research is hard. Keeping this mental health is important. Don't feel depressed because almost everybody feel depressed. But when we talk, we just don't talk about it. Okay. Yes. Yes. Yeah.
My question is, it's like a problem, but
Yes. Yes.
So, but if we just stare at the experiment, like, it's
No. Yes. Right. Right.
So what? So are there things like this model is pretty much like probably like
Yes. 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 Yes.
Once you identify this potential, then like how is carried out. So are there operating your like
Yeah. Yes, yeah. When we were younger, we do exactly what you do, right? But one limitation of using this smart input is the code cannot be used by general audience. So in fact, what we want to do is turn what we know more and more into black box, so experimentalists can use. So they don't have to call me. Jer-Lai, can you explain this for me? I say you use our codes, and so we want to build a ChatGPT for chemical physicists. That's one of our goals, right? But yeah, coming back to the first part of your question, all these observable absorptions, Raman, they only see a very small part of Hamiltonian. They only see these states achievable by 1 photon, 2 photon, right? The coupling is the whole Hamiltonian, right? How important is anharmonicity, right? The energy relaxation is originate from all these dark states that you cannot see, right? Right? They cannot, you cannot see with simple experiments, but they are important for the dynamics, for energy relaxations. So when people study electric materials, all these conductivities, they don't happen emitting photon. Some of them do, right? So how to measure? So I think the first speaker talked about inverse problems. So conceptually, this is also similar. How do we get more information out of these few observables? And what we and as one of the questions, you can also solve directly from first principle, but that's too expensive, right? So there's a lot of room everyone can contribute, either from mathematical point of view or from data point of view. And I think experimentalists need this tool to interpret, not to make serious mistakes in interpreting materials. That's one of our goals. Yeah. Thank you.